what happens to, what happens if we change omega? We have been looking at 1 omega. What happens if we change omega? That is, take this example. This is at 4t. Okay. Now this is the input voltage. Let's say this is the output I am reading. I want to know what happens to the magnitude of the output as I change the frequency. For different frequencies, I want to know what is this ratio. Okay. Studying that is known as frequency response. And typically, we are looking at things like what is the ratio between input and output. And this is a function of frequency. Some books write it as V naught of omega by Vi of omega. Some book write it as V naught of J omega by V naught of I omega. Just notation. Whether you put the J or not in the function doesn't matter. Let's call this input. Let's call this output. So, sir, where does things like this appear? Yeah, quickly, you have a signal here, and there is a signal source here. You're taking some, instead of this voltage source, you're measuring some, body potential, some muscular activity or something like that. There is some processing in the electrical circuit going on, and you are reading the output here. You're removing noise. You want to, enhance certain frequencies based on whether it's, EEG, ECG. You want to enhance certain frequencies. So you want to understand what happens to the ratio of these two amplitudes at different frequencies, not just at one frequency, right? So output or input. This is a very, very important problem, and studying this is known as frequency response, because this is, filters are based on this. Can we filter low frequency, breathing noise? Can we filter AC, current source interference? Can we filter out noise, high frequency noise? Okay. So the key for that is studying this ratio. Of course, there are a couple of more ratios. I have just highlighted one ratio that is known as frequency response, and a direct application of that is filters. Okay, or this RLC circuits will behave like filters.